Oh, I think I need the authority to share my presentation.
Okay. Uh, okay, please try again.
Yeah. Yeah. So, my name is Min-Seung Ko, and I'm working as a postdoc in UT Austin with Professor Hao Ju. And I got my PhD last year in the Yonsei University of South Korea. Then I moved into here. And nowadays we are focusing on the stability issues as well as the flexibility, which could come from the data centers and the large loads such as the crypto mining loads. And in today's presentation, I'd like to focus on the wide area grid oscillations from large-scale AI workloads. So I would like to first start from the gross overview of the data centers. And as you can see from this left figure, this is the demand forecasting from the Berkeley National Lab, and they have forecasted that the penetration level of the data center will be around 10% by the 2030 of the total load in the United States. And um, and when we're considering that the upcoming data centers will be the hyperscale large AI data centers, which have the capacity larger than 1 gigawatt, these kinds of impact from the data centers could be much more larger in some specific regions or specific areas. So as you can see from this right figure, you can see that Virginia, Texas, and California are the most representative three states in the United States in related to the number of the data centers that are going to be integrated into their system. And yeah, and basically, since the data centers require a lot of load demand, the primary issue for the center is that whether the current grid can energize or have condition to energize these kinds of large loads. But after these kinds of data centers are interconnected with the grid, they also pose dynamic stability challenges, very similar to the inverter-based resources. So as you can see from the left figure, the one stability issue related to the data center is their lack of the voltage ride-through capability. And like the right figure, there was also concerns and realistic measurements about the subsynchronous oscillation caused by the data centers. However, if we say that these kinds of tripping and subsynchronous oscillations are mostly focused on the local area, there are some increasing concerns about the grid-wide effects. So in the case of this data center tripping, if the first occurs nearby the data centers, because of the lack of the voltage write-through capability, the data centers will be tripped from the grid. So from the grid perspective, it could be seen as the ramping decrease of the load, which eventually lead to the overfrequency problem in the wide area. And in the case of the oscillation, although the subsynchronous oscillation could be problematic when they are located nearby the synchronous generators, as I'm going to present in the upcoming slides, the wider area of oscillations, which arise at the lower frequency, could be more problematic from the grid perspective. So we would like to model how these data centers, how the demand or demand profile of the data center look like, and we are trying to integrate these kinds of modeling into the realistic system. So when we first look at the data center itself, the overall composition or configuration of the data centers can be presented like this left figure. So basically, they are connected to the grid through the UPS interface, and there are also a backup generator which they can use to protect their own devices when there are some issues in the voltage from the grid. And basically, the most important or the largest part of the data center demand is the server. but you can see that there are also a storage system, networking equipment, as well as the cooling system to maintain the temperature within the data center. So from the current view, the most of the demand for data center comes from the conventional server, which is based on the CPU operation. And also you can see that other type of loads, such as the cooling or storage, takes around 30 to 40% of the total data center. And you can also see that the AI workload or the GPU-based servers takes around 10% of the total data center load. But you can see that in the future, there will be a larger portion of the AI workload in the over data centers. But this proportion is also contains the conventional as well as the upcoming or newly installed data centers. So when we focus only on the generative AI hyper data center, the fraction of this AI workload would be much higher, which could rise to around 50% of each data center. So when we model these kinds of data centers, we need to include all of these components to the data center model. But fortunately, compared to the AI workloads, the non-AI workloads, which would be the CPU-based server load, and the non-server loads show a more consistent pattern than these AI workloads. So we can just assume that these kinds of load are just a constant load, and we focus on modeling the fluctuation of the AI workloads for the oscillation study. And when we see the process, how we use the commercial AI model or the large language models, there are basically three operation stages, as you can see from the below figure. So first, we need to train this large language model initially. Then we need to fit or adjust the parameters for our special use during this fine-tuning stages. And based on this fine-tuned ways, we have finer commercial large language models. And the usage of this finer model is called the inference stages. And during this, in the case of this inference stage, it is very helpful for the industry or the data center owners to locate this inference data center nearby the demand zone of this large language model. So mostly in this case of this inference workloads are separately handled by the separate smaller data centers, which is located nearby the demand zone, which we call as the inference zone. So in the case of the large hyperscale data centers, we can only focus on the training and fine-tuning workloads. And when we look at the power consumption to train these large language models, as you can see from the left figure, in the case of the early type of the large language models, they only require around tens megawatts. But when we look at the more recent large language model, we can say that they require hundreds of megawatts, and this could be even larger for the future large language models. So even if we install the gigawatt scale data centers, the most of its demand will be dominated by the patterns of the large scale training workloads. So to start from the power system load to the AI workload, you can refer to this right figure. So first, the current fraction of the data center load will be around 5 to 10% of the total power system load, but it could be much larger. It could rise to 20 or 30% in the case of the some specific regions. And when we look at each data center, currently the AI workload only takes around 20%, but in the future it could be rise to 40 for 50%. And when we look at the AI workload itself, the most of this AI workload will be composed of the large training load, which are trying to train the large language models. But we would also have some small training load, trying to train the smaller neural networks as well as the fine-tuning load in this blue color. So, as mentioned earlier, for modeling or profiling the power or load demand of AI workloads, we can just focus on the training and fine-tuning workloads. And based on the NERD reports as well as other reports, they say that there was an actual oscillation driven by the large language model training workload around the 1 Hz. So we set the training workload as the fluctuating signal around the 1 Hz. And in the case of the fine-tuning workloads, they are well known that they have they fluctuate at a slightly lower frequency. So we model the fine-tuning workload like this right figure. So basically, both workloads can be modeled as a fluctuating signal, which have a high power dimension and a low power dimension. However, as you can see from these figures, there are a lot of stochastic components at both the intra-iteration and inter-iteration level. So we need to include some stochastic components into these workflows. So basically, for both the training workloads and fine-tuning workloads, we assume that during the high power dimension and the low power dimension, there could be lots of higher frequency inter-iteration variabilities. And when we look at the time scale, these time scales also could be different for each cycles, as well as the basic demand during the power dimension and the lower dimension. And when we compare these training workloads and the fine-tuning workloads, you can see that the fine-tuning workloads are they more resembles the square waves compared to the AI training workloads. So from the perspective of danger for the force oscillation, we think that the fine-tuning workload could induce more severe oscillations compared to the training workloads if they have the same amount of the load demand. However, since the training workload still takes most part of the overall data centers, the overall demand will be dominated by this AI training workload in the left figure. So by aggregating the large training workload, small training workload, and the fine-tuning workloads, we can model these stochastic AI workloads. And basically, so from this left below figure, you can see the general parameter settings, which I previously presented in the previous slide. So basically, the training workload fluctuates around 0.5 to 1.5 Hz. So the fluctuation frequency could be different for each data center as well as the scenarios we conduct. And you can see that in the case of the fine-tuning workload, they have a lower fluctuation frequency between the 0.3 to 0.7. And here, this mu parameter represents the deviation from the high power dimension to the lower power dimension. So you can see that the fine-tuning workload has larger deviations between the high power dimension and the low power dimension. So based on these kinds of mathematical models, we can synthetically generate the AI workload, which are shown in this right figure. So when we conduct the FFT analysis on this generated AI workload, you can see that the dominant frequency part is still located around the 1 Hz, but you can see that there are some modifications caused by the fine-tuning workload as well as the small training workloads. And we also actively working with the AWS and Meta researchers, and they have reviewed our generated workload signals, and it looks, and they said it is very similar to their own experiments and their experience. And we also compare these kinds of measurements with the GPU level realistic measurements, which you can see from this left figure. So you can see that the generated signals resembles this kinds of realistic measurements based on the GPU level. And because the GPU level measurements has a higher and more fluctuations than the data center level, so there could be some more aggregated responses in our generated workloads and signals. So we have implemented this kinds of mathematical models into the WEX system. And basically, we are based on this generated time series data, we modify the load and the location of the data centers at each time step. And we use for the simulation tool, we use the Andes, which is based on the Python. And when we look at the overall penetration level of the data centers, we assume that there's around 10% penetration level. And because since the web system has around 60 gigawatt demand, the data center demand will be around 7 gigawatt. And we assume that the 7 data centers, each with 1 gigawatt capacity, are installed in the web system, as you can see from the right feed. And for each data centers, as we mentioned earlier, the AI workload are assumed to occupy around 20%. So basically, for each data centers, there will be around 200 megawatts of fluctuations. And as you can see from the below tables, we are trying to observe how the oscillation or the magnitude of the oscillation changes according to the various factors. The first factors would be the system level factors, including the inertial level of the power system and the data center penetration level. And in the case of the data center level factors, they could include the individual data center size as well as the range of the fluctuation frequency. And as another data center level factors, we also consider the geographical locations of the data centers. So for all of these previous simulations, we assume that the data centers are located at zone 1A, by concentrated. So in this case of concentrated data centers, they are located far from the locations of the unstable modes, but we also consider the geographically distributed data center cases, which are represented at the red triangle in the right figures. So when we look at the oscillations caused by this AI workload, basically they have fluctuations around the 1 Hz. They mostly excite the local modes in the web system. But as you can see from this left figure, you can see that the generators in this purple zone and the generators in this green zone shows different phases, which means that there is also inter-area oscillations. So this will be the characteristics of this AI workload driven oscillations, which means that there's a inter-area oscillation, but the frequency of this oscillation is mostly located at the local mode frequency. Then we move to how the various factors can affect this kinds of oscillation. And the first factor will be the system inertia. And basically, if the system has a lower inertia, there will be a larger oscillations. But we are trying to analyze these kinds of amplification of the oscillations in a more systematic way. So we have conducted the eigenanalysis on the web system, as you can see from the left figure. So in the basic baseline system, you can see that from the black points, there are some unstable moves around the 1 Hz, as well as the lower frequency around the 0.4 Hz. But when we change the inertia of the system to the lower value, you can check the eigenanalysis results from the red axis. So there are more unstable modes in the lower frequency zone, as well as around the 1 Hz. And you can also see that even the existing unstable modes move to the more unstable regions. So based on this kinds of analysis, you can see that from the right figure in the lower inertia system, there's a larger oscillation happens compared to the baseline cases. And the interesting point could come from this below figures, and this below figure is the Perennial analysis results. So basically, x and y axis of these figures shows the frequency and damping ratio of the measurements at each base, and the size of this circles represent the magnitude of the oscillation. So first we can compare that when we compare this left and right figure, you can first see that there's a larger oscillation at one hertz in the lower inertial system. But you can see that when we compare the magnitude of the oscillation, you can see that there's also larger oscillations in the lower frequency zone around the 0.4 hertz. But the interesting point in here is that in the lower inertial system, these lower frequency modes have a higher damping ratio, and due to it because of the impact of the reduced inertia. And then we increase the data center penetration level from 10% to 20%, and the 30%, and accordingly, as the data center penetration level increases, there will be a larger magnitude of oscillation. And you can check it from this left figure, which shows the FFT analysis results. But compared to the previous case, you can see that from the perennial analysis results, there's no significant difference in the oscillation frequency and the damping ratio in this data center penetration level cases. So basically, there's only a difference in the size of the circles in this case. And notably, this data center penetration level was the most dominant factor compared to the other factors in the amplification of the oscillation magnitude. Yeah, and now we move on to the data center factors, and the first factor will be the data center size. So from the baseline case, we assume that there's the smaller number of data centers, but with a larger size of each, resulting in the same penetration level. So we modify the size of the data centers from 1 gigawatt to 2.3 gigawatt. And accordingly, in the larger data center case, there's a larger oscillation magnitude, but the more notable observation is that the higher frequency components are observed in this larger data center case in this right figure. So, this could be interpreted that the individual data centers affect larger or inject their own higher frequency components into the grid frequency. And next is the impact of the fluctuation frequency. So from the normal frequency range between the 0.5 to 1.5 hertz, we adjusted to range into the narrow range around the 1 hertz, and we also compare the wider range from 0.2 to 2 hertz. So as you can see from this FFT analysis results, as we narrow the range of this fluctuation frequency, there will be a more concentrated and larger oscillations around the 1 hertz, as you can see from this red lines. And generally, so in the wider range, there will be a smaller magnitude of the oscillation at 1 hertz, as you can see from this blue lines. However, as you can see from the right figure, in the case of the wider frequency range cases, you can see that not only the oscillation at 1 hertz, we can also observe the lower frequency zones, which would be around 0.2 to 0.3 hertz. So in the case of this wider frequency scenarios, we should also think about the excitation of the inter-area mode from this data center demand. And now is the geographical location part, and we think that this part will be the highlight of our work. So we first think that the geographically concentrated data centers would affect larger to the grid. So we thought that this could act as a more powerful forcing signal from the grid perspective. So we thought that this concentrated data centers would induce more larger magnitude of the oscillations. but the simulation results told us that the distributed data centers cause larger oscillations compared to the concentrated data centers. And we think that there could be two reasons behind this kinds of observation. So first is that because the unstable modes are dispersed in the wide range of the grid, as you can see from the right figure, so the distributed data centers would have higher possibility to excite this unstable modes stronger. So this could be the one reason why there was a larger oscillation in the distributed cases. And second is that in the case of the concentrated data centers, the overall or the finer power from all of these data centers could be aggregated. So there could be some smoothing effect in the case of this concentrated data centers, unlike the distributed cases. So as you can see from this primary analysis results, there's a larger oscillation in the winners in the distributed cases. And we think that this is because the power smoothing effect in the concentrated cases. And as you can see in this lower frequency zone, although there are some similar magnitude of the oscillations in the 0.5 hertz area, but you can see that there's much lower damping ratio in the distributed cases. So in the case of this flu zone, this should arise from this first factor, which means that the distributed data centers may excite the lower frequency mode around the 0.5 hertz in the wax system. So when we design the geographical locations of the data centers, from the oscillation perspective, the concentrated data centers would be more helpful for the grid compared to the distributed data centers. But in the case of these concentrated data centers, as you can see from this right figure, they're vulnerable to the voltage stability issues. So basically, when designing these locations, we need to consider these counterparts, which are the oscillation perspective and the voltage stability perspective. Yeah. So, fortunately, industry as well as the power system operators and researchers are all now thinking about these issues and try to mitigate these kinds of fluctuations. And I would like to introduce about the efforts from the industry. And in the case of the Microsoft, they are trying to insert the capacitors at the rack level of the GPUs. So in the case of the data centers, basically, they are composed of a large number of legs, and each leg includes another large number of GPUs. So they're trying to insert those capacitors for each leg level, and you can see that there are some more smaller fluctuations by installing these capacitors. And in the case of the Tesla, they have their own the Megapack, which will be a type of the energy storage system. So they also say that unlike this orange signals, by using their own Megapack, they can minimize these fluctuations, as you can see from this blue lines. And in the case of the OpenAI, they also consider the rack level devices, but they try to use the energy storage system at the rack level. So as you can see from this left figure, they say that they can almost reduce or they can minimize the fluctuations by using this rack level energy storage systems. But another point the OpenAI has discussed is that for the rack level energy storage system, it is very difficult to minimize this ramping effect from the data centers. So so the fluctuation of the data centers is also a large problem in the grid, but this ramping behavior, which arises at the start or end of the training process, is also another large problem in the grid. So in our ongoing work, we are trying to mitigate both the ramping and fluctuation issues caused by the data centers. And specifically, we are considering co-located resources, and this resource will be the hybrid solution or hybrid energy storage system using the battery energy storage system as well as the supercapacitors. So basically, the battery energy storage system has been widely adopted for the power smoothing in the wind power plants, but the supercapacitors can provide a faster response than the battery energy storage system. So if you rely only on the battery energy storage system, it could be difficult to handle the ramping issues or the very large bursts during the fluctuations. So we are trying to use this hybrid energy storage system. So while we control this two different types of resources, we prioritize the supercapacitors for the ramping and the first fluctuations. So the other part, which will be the nominal or slower fluctuations, could be handled by the battery energy storage system. So basically, supercapacitors need to respond to the faster deviations. So we need to design the controller of the supercapacitor based on the PD controller. And in the case of the BAS, we can just use the I controller to minimize the errors. So based on this kind of co-located data centers, we can minimize the fluctuation as well as the ramping, like this right figure. So in the case of the ramping event or the very instantaneous large deviations, the supercapacitors take large part of the smoothing, and in the case of this nominal deviations, BAS can do their works. So in the frequency, you can compare that the red lines, which is based on the power smoothing from the co-located resources. They have a much smaller deviations than the baseline cases in the black lines. And as a further consideration for the seamless integration of the data centers, I think we should also consider some basic grid stability improvement. So considering that there will be more and more resources which could induce the fluctuations into the grid, so we should think about how can we mitigate these issues more cleverly. So basically, if we install all the battery energy, if we install the battery energy system, all the supercapacitors for all the data centers or all these fluctuating sources, we can mitigate this problem, but we should consider what would be the more economic solution or more impactful or helpful solution. So in that kind of, as a result for this kinds of grid stability improvement, we believe that East Tech could be the best solution for these kinds of issues since as I have mentioned earlier, there some voltage and frequency coupled issues are arising, and basically East Tech can handle both the voltage and the inertia or frequency stability issues. This East Tech could be a good mitigation issue for these kinds of problems caused by the data centers. And as I presented in the previous slide, we are also trying to locate these data centers nearby the synchronous generators or the renewable energy sources. And we are even considering to insert more resources such as the energy storage system and the supercapacitors at the same point of interconnection with data centers. So we think that there could be potential control interaction in these co-located data centers. And since there's ongoing efforts about the control interactions of the grid forming inverters, as well as the grid following inverters, these kinds of control interaction could be another a big issue in the data center research. Yeah, so to conclude my presentation, so I first talk about the potential wide area grid oscillation, which could be caused by the fluctuating AI data center load. and we are trying to observe how this oscillation modifies according to the various vectors in the grid. And then we propose the hybrid energy storage system to smooth this power demand from the data centers so that the oscillation issues can be mitigated. So for more details, you can refer to our recent preprint in here. And yeah, and this is the end of my presentation. Thank you for listening.